polarization. And what's more, because we've got this different ratio, it's constrained our experimental requirements somewhat. So we have put on this constraint. So what we've shown is that riders can be used to model these properties. So now I will exceedingly quickly scan through other things. If anybody's interested to talk to me about these properties afterwards, I'll take the rest of this stuff offline. But exploring riders, what we're seeing is that we can get intrinsic rotation of properties analogous to spin. Here you're seeing we've got a rider spinning inside a subparticle. So we're getting intrinsic angular momentum built into our particle. Remember that subparticle is intrinsic to the greater particle. It's a little bit dodgy because it occasionally swaps direction, as you'll see. And we've also got a different relationship there. We can also use multiple riders together in order to encode particle variety. You might remember I talked about large particles and coarse graphs. You're seeing one there. I'll explain that to anyone who's interested. But essentially, I used a Richon model to try to encode some particle variety you see in the standard model. And then we basically encode particles so they always travel in groups of big size. And also, very briefly, what we can also do is generate a much more interesting set of relativistic effects that don't require us to have this extra compact dimension. We can use helical paths instead. But much more interesting, perhaps, is the fact that we can use the same technique to alter the geometry of the graph that underpins it, so that we can essentially simulate an extra dimension. So we can take a particle that is traveling in a two-dimensional plane and have it behave as if it's traveling in a three-dimensional space by changing the geometry of the underlying graph. So we can literally synthesize a compact dimension and use that to encode not just relativistic effects, but potentially a large range of different particle symmetries, SU2 symmetry, SU3, whatever we like, and basically use the same sort of Riderstein mechanism in order to locally deform the geometry of space in order to produce a variety of very exciting effects, some of which have sort of jazzy connotations of being a bit like the Higgs field. Looking at these limitations, we've got at least the beginning of starting to nail at least 5 of these limitations, so we're in a good place to move on. So I shall now conclude swiftly as I can. We've got a robust model for creating interesting superparticles. We've got a model for particle complexity, simple extensions to the basic jellyfish, very minimal extensions. We've got a way to put further constraints on our predictions of spatial granularity. We've also got promising models for relativistic effects, and we're well positioned to start removing other model limitations. We've got the beginnings of self-interference and wave attributes, which turns out to be doable, but very, very expensive. I'm still looking for a way around that. We've got background independence. The work there is showing promise. We seem to be able to create graphs that spontaneously generate dimensionality at large scales. And we've also got some beginnings of an interaction model, although interaction model is easy to put one together, but very hard to get it right. So also one would hope is that this kind of research might yield some answers to interesting physical questions, such as, why do attributes like spin occur in nature at all? Why do seemingly point-like particles have intrinsic angular momentum? It may be that looking at things in terms of sets of nodes like this on extremely discrete structures will perhaps give us a way to sort of answer why patterns like this occur at all. And also, why do group symmetries for particles occur? Why a great amount of what happens in modern physics relates to these group symmetries being absolutely critical? Well, by defining things in terms of these very simple algorithms, in terms of sets of nodes, iterating using very, very basic functions, we may be able to start taking a poke at that question too. So that's pretty much it. I've covered all my material, so all that remains is to thank you all for listening, to thank some of the people who supported me from UCSC in my endeavors, and to say there's my email address, and if anyone wants to look at these video shorts that I've used, some of them are currently available on YouTube, and the rest will be going up shortly. So that's about it. Thank you very much.